For problem 6, we will consider insulating cylinder with charge Q that is uniformly spread over the volume, The radius of this cylinder is A, it is given, and the charge is given, it is Q. We need to find electric field, everywhere. We will use Gauss's law to find the electric field everywhere. E dot ds is Q enclosed by epsilon naught. Our first region where we are interested in electric field will be inside the cylinder. R is less than A. The Gaussian surface, because of cylindrical symmetry, will be another cylinder. This cylinder is located at the center of the original cylinder. This is imaginary Gaussian surface, our imaginary cylinder. The radius of this cylinder is arbitrary r, that is less than A, and the length of this, the height of this cylinder is L, arbitrary L. So let's apply Gauss's law. Because of the cylindrical symmetry, my E is at each point, my electric field is in the same direction as area vector. The electric field has cylindrical symmetry. E is the same at each point of this cylinder, so I can take it out of the integral, and then integral ds is S, where S is surface area of this cylinder. We are not, the flux out of this top cap and bottom cap will be 0, since electric field is radially out, and area vector for the top and for the bottom is up and down. All we are interested in is this side surface. Area of this side surface is 2 pi r L. This is the left hand side, and flux through this is 0, flux through this is 0. We wrote total flux through this cylindrical surface. It is equal to 1 over epsilon naught, charge enclosed. Charge enclosed is Q enclosed is charge density, charge per unit volume times volume. Charge is uniformly spread here. What is charge per unit volume? Rho. We are looking for this original cylinder. Charge per unit volume is Q divided by the volume of this cylinder. I forgot to tell you that the length of this cylinder is given. It is capital L. So Q is given, A is given, and L is given. 1 over epsilon naught rho Q divided by the volume of this cylinder. What is the volume of the cylinder, of the original cylinder? It is pi A squared times L. This is rho. It doesn't change. It doesn't depend on the choice of our Gaussian surface. This is just a charge density for the original cylinder. We have Q divided by pi A squared L. This is rho, charge per unit volume, times volume enclosed by this Gaussian surface. What is the volume of this Gaussian surface? It is pi little r squared times L. This is V. Rho V is charge enclosed. Now what will be the electric field? We are ready now to write the electric field. The electric field is, let's simplify it, pi and pi cancel out. Then arbitrary L is gone, as it should. And then R here and R squared here. So I have 1 over 2 pi epsilon naught. Then I have Q divided by A squared L. And I have still R here. So the dependence is my electric field is proportional to R. And the direction is radially out. So let's put in parentheses radially out. Now we need to find the electric field at R greater than A. I will consider new Gaussian surface. This time I will do it in green. My new Gaussian surface will be this cylinder, again with the center at the original cylinder. This is my new Gaussian surface. The radius of this is again arbitrary R that is greater than A. The left-hand side of the height is again L, arbitrary L. So the left-hand side, with the same argument that we will have a non-zero flux of electric field just out of the side surface of the cylinder, I have E times area of the side surface, 2 pi RL. No changes here. And then I have 1 over epsilon naught rho, which is unchanged. It is charge divided by pi A squared L. This is rho. And then volume of the charge enclosed. But where is the charge? The charge is just within this radius A. This is the volume with the charge. So what is the volume where the charge is? It is pi A squared times L. I cannot go to R because there is no charge at R greater than A. So I put pi A squared L, and this is my charge enclosed. So what will be the final expression for the electric field? E will be equal to 1 over 2. Let's cancel out this pi. L is gone, as it should. And then I have 1 over 2 pi. 1 over 2 pi epsilon naught. Q divided by A squared L. Oh, I'm sorry, A squared and A squared cancel out. Q divided by L. And then I have this 1 over R dependence for electric field outside of the cylinder. And it is radially out. So inside the cylinder, if I plot this electric field E as a function of R, let's just consider R to the right, then inside my electric field is proportional to R, and outside of the cylinder it behaves as 1 over R. And at this point, when little r is equal to A, the magnitude of electric field is Q. So this point is Q divided by 2 pi epsilon naught, Q divided by 2 pi epsilon naught L A. We found the electric field created by this uniform distribution of charge within the cylinder of radius A and length L. We found it everywhere. The electric field at R less than A is here, and the electric field for R greater than A, the answer is right here. We found it everywhere. I need to remind you that this is a very long cylinder. So we have found the solution far from the edges where we can use this cylindrical symmetry that is absolutely crucial for our use of Gauss's law. So that's why we say that the cylinder is very long. We found the electric field right here, far from the edges, far from the region where the lines of electric field are disturbed and do not have cylindrical symmetry.